we on? Oh, should I start? Okay, so this time I'm going to start out doing something that sounds totally different from last time. Last time I talked about the magic of free fermions, but this time I'm going to start out talking about the 1 plus 1 dimensional Ising model, or the quantum Ising chain, which we will then see very quickly that is exactly the same problem as I talked about last time, free fermion system, although, well, there's some major subtle things that we'll talk about. So anyway, so in general, we'll talk, so the Ising model is an example of a spin system, and in particular, so a spin system is something where the degrees of freedom typically in a quantum system, we have a two-state system. At every site of some lattice, again, we're going to be one-dimensional. People will often say this is spin a half, but I won't really ever use that because I'm not going to talk about systems in general that are SU2 invariant, but still that's a common word that's used. And so the Hilbert space, so let's now do a spin chain, a quantum spin chain. It's always good to define what you're doing. So we have a Hilbert space that's a collection of space systems. Not coincidentally, just like last time. If you want to be fancy mathematically, then the Hilbert space would be some two-dimensional vector space where we act with the complex numbers, tensored with a bunch of other ones corresponding to each site on a chain. And we're going to talk today both about periodic and open boundary conditions, but when we get to the Hamiltonian, I will discuss that. So, all right, so let me now, I didn't write down Ising yet, so today's lecture will be mainly on the Ising spin chain. And often called the transverse field Ising model. And I'll explain today why also this gets called now the Kitaev chain, as I mentioned briefly last time. So let me say just two words about the actual Ising model. The reason I'm calling this the Ising spin chain. So the Ising model is some 2D or any D, but let's talk about the 2D classical Ising model. One of the most important models in statistical mechanics. And so what it is some model of some lattice. I can usually only just draw the square lattice, so let's draw a square lattice where you have some spin that's up or down at each point on the lattice, and then there's nearest neighbor interactions. I won't even write down the energy. Probably most of you have seen this before. But the reason I'm drawing this, so this is the lattice. Well, let me just draw it like this. This is the lattice at every point. There's this spin. And they interact with each other, and you compute the partition function, correlating functions, and all that stuff. But again, most of you have probably seen the most convenient way to compute a partition function is the transfer matrix, which says basically I start with a bunch of spins in a row, say. My transfer matrices I like to make go vertically. So I start with a bunch of spins in a row, and then to compute the partition function, I add one row at a time. And I can write all this out, and if people want, ask me, and I'll write all this out. But since this is just motivational, I wasn't going to. And you add one row at a time. And so the reason I'm saying this is because now what you think of this becomes this vector space. Again, you think of the transfer matrix, it's always important to say where are things acting. And so you have some vector space, which is, if this is length L across here, the transfer matrix of the classical system acts on this 2 to the L dimensional vector space. And not coincidentally, it's the same vector space. And so that's how you work out a classical model. Well, there's a correspondence that works, well, for many, many models. Not every single quantum spin chain you're interested in looking at, this will happen for. But for many, many of them it does. And this is no exception. So if you have a transfer matrix, which again, ask me, well, maybe tomorrow afternoon, if someone wants to see me write all this out, I will. We have some transfer matrix that's building up the partition function, but it turns out you can take a limit of the transfer matrix. So in some limit, the transfer matrix is close to the identity matrix plus some correction. So this is some small parameter, small coupling. Those of you who know the Ising model, it's related to the jx and the jy's on the various links and tuned to a particular value, plus something here. So this is an operator acting on a vector space, and then this is another operator. So it turns out you can do this here. But then if you do this for the Ising model, you get the Ising spin chain. If you take this certain limit, which that I didn't define precisely, but I'm just giving you the words and telling you the answer. And so what you find for the two-dimensional classical Ising model, you get the following relation. And for the moment, we'll take periodic boundary conditions. So that means anything, so sigma A L plus 1 equals sigma A L. So I'm going to define all these things momentarily. In fact, I'll define them right now. So, okay, they're acting. Let me leave that up because these operators are acting on this space. And what these operators do is the following. They're just Pauli matrices, but you got to be careful that they're acting on this whole space. And so what sigma, well, A for the eighth Pauli matrix sub J is really the following operator. It just acts as the identity operator on most of the sites, but then on the jth site, it does whatever the Pauli matrix. So if it's sigma z, it's 1 and minus 1. Everybody knows the Pauli matrices. Reason I'm being pedantic here, I don't know if there's any mathematicians here, but if you ever talk to mathematicians, and physicists will just say, oh yeah, this is the Pauli matrix acting on the jth site. And they say, okay, I understand, that's a two-state system. But then you say, but this makes no sense, it's acting on vector space, right? So the important thing is each sigma j acts on all the sites. It just does something non-trivial on the jth site. And that sounds like I'm being pedantic, but if you want to infuriate a mathematician, it's very important to them to understand where operators are acting on, and it's actually important to us. And if they say that to you, and then we go, yeah, of course we mean it just acts as the identity everywhere else, but that's different. I mean, it's a different space. So I'm being pedantic, but this is useful. If you get nothing else out of this lecture, always when you write down an operator, say what it's acting on. That's all. That's all. It's not that hard to do, and it makes our mathematician friends much happier. Anyway, all right. So I'm being pedantic, but I wanted to show up. But okay. So the reason why I introduced the Ising model is something interesting here. You know, you're always taught that. When you're first taught quantum mechanics, it's this great generalization of classical mechanics. You know, you replace a Poisson bracket with a commutator and you turn numbers into operators. Well, that's all correct, but what I just showed here is actually the quantum theory is a limit of the classical model, not vice versa. Right? Very important. The classical theory is more general here. So if you go to one higher dimension, so the moral is you go to one higher dimension. So I'm talking about a two-dimensional classical model. Now I'm doing a quantum model in one dimension, with that Hamiltonian. So once you add the extra dimension, actually the quantum is a limit of the classical. The classical is more general. So I say that's not true for all quantum systems, or at least I don't think it's true. I don't know if you can ever prove that statement. But anyway, it's not obvious what the one higher dimensional was in all cases, but in pretty much every case we ever look at. And that's why we always have this mismatch between condensed matter and particle theorists. They always give the space-time dimensionality, so they would call this the two-dimensional model, and rightly say this is just some stupid limit of the two-dimensional model, and a condensed matter person would say this one-dimensional. Same thing, but important points to make. So being a little pedantic here, but I wanted to that. All right, so this is now the specific Hamiltonian. So we can forget the two-dimensional classical Ising model after I just make a few comments. Notice where this comes from. Well, this J term just says it wants to put an interaction between the two nearest neighbor spins. And I put, by convention, the minus sign in front. So if J is greater than 0, it's a ferromagnet. So that means the energy is lowered when the two spins next to each other are aligned. But now a relic of taking this limit of the 2D classical model is that, of course, when I go from this row to this row, the two spins don't have to be the same, and I get a different energy depending on whether the two spins are the same or the two spins are different. And that's that term right there. So this is why I said people sometimes call this the transverse field Ising model. This looks like a magnetic field, but a magnetic field in the x direction. So I tend to not call it that because there's also the longitudinal field, and that sounds nasty, so I just call it the Ising spin chain. Or like I say, we've learned now, it's now the Kitaev chain. One more comment about the model before discussing how to solve it. I guess, okay, I've belabored that point enough, so we can erase that. There's a Z2 symmetry of this model. And so basically, you can again see it from the original classical model, if you just flip all the spins, if there's no longitudinal magnetic field, there's no sigma z j term. So that's this is Z2 symmetry if there's no longitudinal field term. And so the symmetry generator of this, I will name completely incomprehensibly for the moment, but in a little while it'll be clear why I've named it -1 to the f, is then just the product of all the sigma j's. You flip all the spins. So that commutes with this Hamiltonian. So that's really the only obvious symmetry of the Ising model, Ising's spin chain. I'll try to always say Ising spin chain, but when I say Ising model, I mean this too. Okay, good, just setting up, like I say, somewhat pedantically, but I think it's important. All right, so one of the great mysteries of statistical mechanics, and maybe one of our great embarrassments, is we have this unbelievably fantastic result. Is this model is really easy to solve, and I'm about to do it, and still to this day has this unbelievable reputation of being difficult to solve. And in fact, so I'm going to solve the spin chain, which is really easy to solve. It's a little more work to solve the full classical one that I wrote down originally, but not much. And if you set it up right, it's only barely any more work. It just takes a little finesse in setting it up right. But this one, even once you know the trick, which I'm about to show you, so it's an embarrassment that people think this is hard, but it's not. It's really easy. And so I'm going to describe how to do that next. And so you can try and tell all your friends to finally end this myth that it's somehow a thing. I mean, it was a feat when they did it. It was brilliant. But, you know, like most things that it was brilliant when you did it, you know, we learn how to simplify. And then once you learn the right thing to do, it's not tricky at all. So the trick is, right, why I started out with free fermions in these lectures, is this model can be mapped very easily onto free fermions. And the usual name to this, given these days, is called a Jordan-Wigner transformation. I've never read the papers. Has anyone in this room ever read Jordan or Wigner's paper? I think they're only in German. I don't know if they've ever been translated. Has anyone read it? So someone someday, please, I always ask this, someone read it, please, and tell me what Jordan and Wigner actually did. Probably, I don't speak German. I could probably read the equations, but that would require my actually digging up the paper, so I haven't even done that yet. But somebody please do that. I mean, I've seen it referred to hundreds of times, but I'm fairly confident no one. What? I have no. Like I said, I just have no idea what they do. I don't even know who named it the Jordan-Wigner transformation. Somebody named it at some point. Jordan wrote a paper. Wigner wrote a paper. Somebody at some point named it. I don't even know. I have no idea who named it the Jordan-Wigner transformation. I'm assuming they did it, and the reason why I'm belaboring this is for the Ising model. They didn't do this for the Ising model. So the original work for this. So Onsager, quote, solved the Ising model, and by solved I mean computed the complete spectrum. And he did it this fancy way by doing something called what people call now the Onsager algebra. Turns out his algebra is just the algebra fermion bilinears, but he didn't know about the fermions. He just figured out the bilinears. Real tour de force if you go through his paper. It has this reputation. It's a bit technical, but actually it's very clear. If you go through the paper, you just have to stay with him, but it's actually quite clear if you're patient. So that's how he solved it originally, and then a few years after that, what they called assistant in those days, Kaufman has no, just want to, his assistant, I think what they call in those days, she was more or less his postdoc, against his express, he told her he thought it was too complicated and so she shouldn't do it, but she actually figured out what now we would call this map to free fermions. She did it, again, sort of, she did it in terms of spinor representations of O2n, so again it looked a little bit off-putting, and this is why the Ising chain got this reputation as being really hard to solve for the Ising model. But mid-60s, in fact, famous review article by Schultz, Madison, Lieb, different one than the one I mentioned last time. This is a Rev Mod Phys in I think it's 64. Made it all just completely, utterly clear. I have no idea, again, why people think this is complicated. That paper is just so beautiful and so easy to read and just makes it clear. So I'll just so they're doing, again, the full 2D classical model. It's even easier if you specialize to this quantum spin chain limit. All right, so that's some historical comments. But anyway, so that's who really did it for there. Like I said, I honestly don't know what they did. But so here we go. So what they say is, so I'm going to write it out in a slightly different language than I think Schultz, Madison, Lieb. I'll write it out what people now call the Majorana basis. But you define the following operators. Well, let me write it out and then let's talk about it. Okay, so I'm in a system with L sites, but I'm going to define for each point in the original system 2 operators. So I can draw a picture like this, if you wish. So this is each site. So this is, say, the original site j equals 1. I've got that. So it's not a typo that I'm using the same j here. I mean the same thing. And then this would be psi 3, psi 4. And so on. Okay, so these are just operators on my same Hilbert space. That's why, again, being pedantic, but it's just a bunch of operators. But these are non-local, well, at least the one you get far away, because I've got this string. So that's what people often call this thingy. This is a string. So if you wish, in terms of the spin language, what happens if I have some operator here? Well, it measures the spin on site J, but then flips all the spins behind it. And so this operator, the other one at the same site, well, does almost the same thing, but flips the spin on the site here. So notice it's less than or equal to. So also flips the spin at the site. Okay, so they're just a bunch of operators. But the beauty of these things, which I presume, let's leave that up, is what Jordan and Wigner did in some language or another. They were probably thinking the Heisenberg model, but I don't know that. So what you find when you define these operators is something really magical. So first of all, they all square to 1. Each of these operators square to 1. That's why I put that I in front of the second one, so that that thing squares to 1. They're Hermitian. Again, that's pretty obvious. Again, the I's there makes it Hermitian. Oh, and I forgot one important thing. I forgot the J right there. Okay, and then those are both pretty obvious, but then after a few more seconds, what you see is that, well, on the same site, they square to 1, but on different sites, they anti-commute. And that's the beauty of this string here, because if I have an operator here with its own string, well, if I move that through there, the sigma z at the end anti-commutes with the sigma x from the string, and then you get a minus sign. So, in other words, psi a psi b equals minus psi b psi a. So that's just beautiful observation, presumably due to Jordan and Wigner. Or I should say Jordan and or Wigner. That you could make these operators. So same model. We haven't changed the model, but I'm defining a bunch of operators. But then the miraculous thing is, if you now try and rewrite these guys in terms of the size, something really nice happens. Which is, oops, where's a good one? Let's try. You get a fermion bilinear. So in fact, it's easy to check. Well, sorry, maybe I shouldn't have erased it till writing this down, but those things I just wrote down, you can easily check that sigma xj is equal to I minus I psi 2j minus 1 psi 2j. Sorry, I really wish I hadn't erased them. But that's pretty obvious. Remember I said that one of them, they both have the strings, so the strings cancel, but one of them had the extra spin flip at the end, and so that's why you get that. And if you pay attention to the signs, that's what happens. And then for the sigma z, on different sites, you get the bilinear. Now that's a bilinear that stretches from there to there. So if you wish, using this sort of picture here, I can write it like this. So if I do this, so I can, I don't know, write, that's the H coupling. This is the J coupling. Right in there, so I can then rewrite H equals minus, J equals 1 to L, sigma x and one subtlety, well, yeah, we're never going to use it, so I'm just going to say it. So it's actually, there's one subtlety for the last one. So this is actually not quite the same as that. This would, oh, sorry, I wrote the same thing down again. It is completely exactly the same. I've proved rigorously that these two are the same. Sorry. What, sorry? So, I would say, do I need to say anything about, I would say maybe to avoid the minus sign at the end, I'm going to go to I'm going to go open boundary conditions soon. So let's now go to open to avoid the subtlety. So what happens is there's a minus sign subtlety at the end, but it's not, we don't need to ever deal with that. So now let's do open boundary conditions. So let me write it like this. So now it's not rigorously the same. All right, so you don't have to erase what you wrote before. That was periodic boundary conditions, but now it's, let me do open boundary conditions to avoid the subtlety. So again, I keep wanting to write that. Okay, I think I even got the signs right. And so you notice, the only difference between open and periodic is there's now nothing connecting the nth spin with the first spin. So yeah, so to keep drawing this picture here, so H is, so what was just the spin flip at a site becomes this fermion bilinear for the two fermions associated with each site of the original. The J is then will connect the two different sites. So. As a quick remark that will become important probably next time, maybe I'll get to it at the end of this time. Note, in fact, I could let these couplings vary in space, and this would still be a sum of bilinears. I'll belabor that point later on. Oops, and I screwed that up. Any other screw-ups? Look good? So any questions on what I just did? Well, so as I stressed last time, so now I've already come back. Yeah, good, before the hour's even done. So we're actually almost done solving this model because I've written in terms of fermion bilinears, and I did a long song and dance last time saying that any time you have a Hamiltonian, it's a sum of fermion bilinears. Again, nothing to do with Fourier transforms, anything like that. You can reduce this 2 to the L dimensional Hamiltonian. So this is a 2 to the L dimensional matrix. So if you want to write this out in the basis, 2 to the L by 2 to the L dimensional matrix, because there's L sites, two-state system on every site. But then I do exactly what I did last time. So if I now consider some bilinear, yeah, okay, we can lose this now. Let's not. So if we again write down some linear, again labeled by some k will turn out to be momentum if we want to have translation invariance. But if we write some k as some linear combination of these Majorana fermions, so now I can name them. I'm in Italy, so these are now what people call Majorana fermions. These things that are self-conjugate. I'll relate them to the C's I wrote last time in a minute. Okay, so I take some linear combination. Notice there's 2L of them. That's not a typo. There's 2L of them because I had 2 for every side of the original lattice. And then I take the Hamiltonian with it. Well, H is this combination of bilinear. So remember, you commute a bilinear with a linear. The only thing you can get is a linear back, or you can get 0. But the only thing you can get is a linear back. And if you work it out, what I get right here is the following. So let me erase now my algebra. But using this algebra, the fact that they square to 1 gives me the following. So I have this psi 2L. Let's just get rid of this. If I did it right, and so forth. So alternating down this first off diagonals times A1, A2, A. So that's all. So it just gives me these linears back. And in fact, for those of you who actually worked out the homework problem, or maybe I even wrote it out, I can't remember now. I think I did write it out last time. This matrix is exactly the same form as the one I said to do for the staggered free fermions, right? Did I write it out last? I can't remember now. I gave it as a homework problem, but I didn't even write it out. Remember, this was like t plus s, t minus s, t plus s, t minus s. So we're done. I mean, using what I said last time, because by the same arguments, we have a complete set of these raising-lowering operators for this model. So we know all the eigenvalues of this form, this plus or minus form. So in fact, you look at this matrix, it's easy to see that the eigenvalues come in pairs, plus and minus k, so that, again, you get at the end of the day, H is just the sum of plus or minus epsilon sub k, where k equals 1 to L, and epsilon, so 2 epsilon k are the eigenvalues of that matrix. Last time the matrix was symmetric in Hermitian. This time it's anti-symmetric in Hermitian, but then that's easy to adapt the solution from that one to this one. Right. So yeah. Well, when you're writing out things, things. In fact, I'm gonna rewrite this in terms of Dirac fermions in a moment. So in terms of the matrix diagonalization, well, there's the slight difference, the minus signs, but that actually doesn't change the eigenvalues any. So basically, no. I mean, mathematically, it's the same. Yeah. It's a slightly different setup that got you there, but really not. And if you don't like Majorana's, you can rewrite them in terms of Dirac, and you get the same answer. The matrix will change around, but of course it'll have the same eigenvalues. Or if you don't like original, if you like real fermion, yeah. So good. Any more questions? Yeah. Yep. Yeah, so, right. So what you'll see, in fact, to go on Slava's question, you'll see what happens. There's going to be some I's in here. And so these will form various combinations that are like the C's or C daggers. And so one thing that will happen, so you'll see for every eigenvalue epsilon of this matrix, it's easy to show there'll be another eigenvalue of minus epsilon. So you'll, by diagonalizing this one matrix, so notice this is a 2L by 2L matrix. Last one was an L by L. And so then, you got as one set of if you wish, the right eigenvectors were, say, I forget how those were the raising operators, and the left eigenvectors are were the annihilating operators. This one has 2L, and so you have all of the raising and lowering operators there. So it all follows. It's not completely obvious, but you just work it out and write it down, and it all works. So, right. No, these are good questions, but just not. I hope last time motivate. Anytime you get the situation, you always get an answer. And yeah, at the risk of screwing up, let me write down what I think the answer is. In this case, what it turns out to be I think I got the factors of 2 right, but I maybe didn't. So yeah, well, did anyone do the homework problem? You want to tell me what you got last time in terms of T and S? Someone, yeah? Did anyone do the homework problem? You did? Okay, good. Well, what did you get for the? Yep. T and S, yeah, just give me in terms of T and S. That was the homework problem I gave. Good. Everyone agree with that? At least up to 2s, and there's some conventions what you want to choose for k. Because I broke translation invariance and when I put the s in, so it's really translation only by 2, but so k is conventional. But this, I think in this convention's k still runs from minus pi to pi, I think, in that convention. All right, well, someone did it. All right, full credit for you. All right, someone else did it. Good. All right, two of you did it. All right. I got a reputation as being a harsh grader back when I was teaching all the time. Okay, so that's the answer. And then if you plug in, it's actually not obvious. I had a panic this morning when I wrote down the answer in terms of H and J, and I didn't think they were the same. But actually, up to redefinitions of K, what you get, and it's to do with the fact that this is 2L by 2L, and that's L by L. What you get is, again, up to 2s, which maybe I screwed up, but and the k here is off by a factor of 2. The k there, if you want to check this, that was my panic. You get that. Okay, so you're done. So we've solved it before the hour. And that was with a lot of pedantic nonsense that I just kept inserting. If I'd actually just done the calculation instead of talking so much, it would have been probably about a half hour. So we've got the entire spectrum of the two-dimensional the one-dimensional quantum chain. And when I say with setting it up, it's not hard to get the full two-dimensional one. It's a little more. So all the eigenvalues of the transfer matrix and then compute the transfer matrix. So it's there's a 1.5 million subtle cool things you can do. I just wrote a 45-page paper being subtle about the Ising model, so it's remarkable in the year 2016. There's still some interesting things to say about the Ising model, and some of them there. So let me think. Yeah, so ask some questions and then we'll break. A good break. Oh, it's when H is equal to 0, there is no K depends. Yeah, that's right. Yeah, that's right. I've only been going on for 40 minutes, not for an hour. That's right. I started. So good. I'll keep going. Right. So we did this even with the nonsense. We did it in 40 minutes. That's right. And so what happens? And I'm going to talk. Let me defer that like 5 minutes, and because I'm going to do that case specially. Yeah, because what happens if H is 0? The Hamiltonian's diagonal. I guess the Hamiltonian's not written there. Remember, if H is 0. It's all just sigma z, so you can H is just a diagonal matrix, so you don't need any k's to diagonalize a diagonal matrix. So that's basically, yeah, that's right. So good, that's a good check that formula is correct. That's right. Right. So it's just a diagonal matrix. So, when I said diagonal matrix, the Hamiltonian is a diagonal matrix. Yeah. So this thing makes it, much more complicated than it looks. It's that one you don't need anything fancy. So the Hamiltonian itself is just a totally diagonal. In fact, let's, since I was going to do that in a few minutes anyway. Let's do that now. In fact, yeah. Okay, good. Let's do that. So let's go to those limits. So yeah, that'll be a good thing to do before the break. So yeah. So it's always good to go to extreme limits. All right, and one of them is, let me do because I'm more interested actually in the H equals 0 limits. Let me do the J equals 0 limit first. And let's forget fermions. I'll write it out again. So J equals 0 limit, the Hamiltonian is just the sum over H sigma x. Right, so we can all solve that. Again, nothing fancy needed. We can it's just, you have to diagonalize sigma x. So if you work like we we usually work in the sigma z diagonal basis. Let's write it out as the following. So there's lots in this problem, there's lots of pluses and minuses. So let me, instead of using pluses and minuses for the spins like I did before, the two spins are, what we'll call them up and down, U and D. All right, so just to satisfy things. So then, in this j equals 0 limit, right, so then the ground state in the j equals 0 limit is just the linear, it's just a single state, but I have to use these linear combinations. And then I put a minus sign here. All right, so I just diagonalize sigma x on every site. Important statement, this ground state is unique. There's only one ground state. I have to diagonalize each of those terms in the Hamiltonian. Okay, so that's the j x equals 0 limit, which is really easy. Sorry, the j equals 0, no jx, sorry. The j equals 0 limit. So now let's do the h equals 0 limit. That Hamiltonian is even easier to deal with. Sigma zj plus 1. All right, so that one, that's what I did. So that's just a diagonal matrix. So any diagonal, any entry that's not a linear combination of the u's and d's is an eigenstate and has that eigenenergy. And so the ground state, the lowest energy state, well, I can take all ups. So let's take j greater than 0, just to be simple. And then all downs also works. So there's two ground states. So there's a famous result in the Ising model, which I probably won't say much here unless people beg, so you can beg, is there's this duality in the Ising model that supposedly takes the low temperature phase to the high temperature phase. I shouldn't say supposedly, it does. But on the other hand, there's a very clear difference between the low and the high temperature phase here, or the ordered and disordered phase in this language. So over here, there's two ground states, and over there there's one. So duality is true and amazing, but it's subtle. It's not really a duality. The dual is not the original. Anyway, a digression, but I can say more about that later on if people want. Okay, so those are the two limits. But then the interesting thing now is, let's leave this up. Okay, so now we ask what happens when we turn these things on. When we turn H or J on? Well, the answer is not very much. If you make H very small, the true ground states are almost like this. Now, there'll be a term, because you add this term back in once I turn on H. This won't be exact ground states because I flip spins, of course. But if you look at the actual ground state wave functions, they'll be dominated by that. And we can look at the actual ground state wave functions. I didn't explain this much, but using those raising and lowering operators, you can write down the exact ground state wave functions. But they'll be in K space, and it's a little work to see how they look in position space, but it's all doable, and, well, not just doable, been done by many people. So they look basically the same. So the physics of this now that you get is the following. If I just draw my phase diagram, well, it looks like this. Sorry, let me tie my shoe to avoid embarrassment. So there's a critical point in the middle, and from the exact solution, we can see that right away. So for the same reason I talked about last time, well, so with this dispersion relation, or with this epsilon definition of the epsilon k, what happens is if you look as a function of k, we had a discussion about this last time. So if I sort of transform k equals pi to 2 pi back to the original, the thing looks like this. And notice there's no there's no chemical potential here. That's all I take for my Ising model. There's nothing else to do. So I fill this C here, but then there's this gap. So it's gapped unless it's easy to check. Remember last time it was S equals 0, and here that condition is H equals J. Because remember we had T plus S alternating with T minus S along those off diagonals, so now we have H to HJ. So S equals 0 corresponds to H equals J. And what happens at H equals J, you just plot that out, is that at H equals J, they'll come meet like that. So then, that's the one place where there's criticality. So there's gapless excitations. So those goes with criticality. And so this phase, so remember here we had 2 ground states. Well, so what happens here, I'm trying to say, well, this I'm going to discuss maybe in the second half, or maybe I'll start it here, we'll see. So what happens here is, there's just the 1 ground state. So now what happens when we turn on H is is extremely interesting. It's going to occupy us for a while today. So these two things, like I said, aren't the exact ground states. But actually, let's write out what happens. Okay, so this is now boring. This phase, we're not going to say much about it. This is disordered. But let's talk about what happens over here. Well, so at the extreme point, we have these 2 ground states. And they're exactly degenerate. Now we turn on this H, and it turns out there's 2 ground states that split in energy, but only slightly. And we're going to make this, after the break, I will make this very quantitatively precise, but let me set up qualitatively what I'm going to do quantitatively after the break. Okay, so we've got 2 ground states. We turn on this sigma x term that flips. So obviously these are no longer eigenstates of the Hamiltonian anymore. But what happens is we still find, so now let's just go up to here. So H greater than 0, but then less than J. So then what happens, spins start to flip, but you still find order in the following sense, in that if I compute a 2-point function, sigma j prime, and let's now take the limit j minus j prime is large, but still much smaller than the size of the system, because I don't want to deal with finite size effects yet. Well, then this will go to some constant. And we can even call this constant the magnetization squared. Oh, sorry, sigma z, yeah. So I'm used to the classical model. Yes, thank you, sigma z. So I'm just asking the question, 2 spins on sites j and j prime, what happens when I bring them far apart? Well, it goes to a constant, I'll call that m squared. So you notice what people will usually say in the situation is now, if the system gets a magnetization, we have to be a little careful in that. I haven't done anything to break the up-down symmetry. So if I really still wanted to compute sigma zj with the open boundary conditions I've used, this is actually 0, right? There's still an equal probability any given spin will be up versus down in this situation. It's an important subtlety, again, people usually blow off, but it's worth commenting. But if I define it this way, this is well defined, without adding a little magnetic field to single out the vacuum like you do in spontaneously symmetry breaking. Okay, so this is an ordered phase, and people will usually call this spontaneously broken symmetry. So and that's, even though in this situation, like I was just pedantic about, that's strictly speaking not true. Well, not necessarily true. And so now the actual ground states, so let's do something useful here. So this Hamiltonian that I wrote down commutes with -1 to the f. So let's go, remember -1 to the f was this spin symmetry, which I wrote as sigma xj. What else? It's the operator that flips all the spins. Well, now I did this mapping in terms of fermions. And remember, sigma x was the product of the sigma x of j was the product of the two fermions on that site. So what this operator is in terms of the fermions, it's so it's the product of all of the fermions, all 2L of the fermions. And so then you see what happens now, why I called it -1 to the f. Well, it's just a product of all the fermions. So if I take it with any of the individual fermions, it anti-commutes. Because you think about it, it's a product of all the fermions. There's an even number of fermions. It anti-commutes with all of the other fermions, but of course it commutes with itself. So it's anti-commuting with an odd number of fermions, and thus we get 0. Do you want me to write that out? Was that too many words, or is that sufficiently obvious? Just check if it's not. So anyway, so this operates. So now what it says, well, this still commutes with the Hamiltonian. And so what we should do now is take these two ground states and diagonalize them with respect to -1 to the f over h. So I said -1 to the f over h. Just diagonalize them with respect to -1 to the f and h. Since they commute, I can diagonalize them both. So at h equals 0, the two ground states are then plus, plus, plus. Oops, I said u. Made a big point of saying u. Sorry, u's and d, and then u minus d. I guess put a 1 over square root of 2. And let's call this state plus, and that state minus. That's why. And so we have -1 to the f on u equals u. Sorry, plus, well, whatever was true. And -1 to the f on minus equals minus that. So that's obviously true there, but now we move away, we add h in, and this still remains. So the ground states aren't exactly this, but there's still these two almost ground states. But away from h equals 0, these become exponentially close but split in energy. And by exponentially close, I mean something e to the minus alpha L, where alpha is positive and L is the size of the system. And after the break, so now we'll take a break. After the break, I'm going to make this statement very precise. Okay, good. So see you in 10 minutes we usually wait? Yeah, okay, good. Okay. Okay, good. Let's start. So now some of those maybe vague sounding statements I made at the end of last time, I'm going to make very precise. Let me say one important thing that I didn't make clear in the first hour. When I drew this dispersion relation for Ising and said use the T plus J results, that's for periodic boundary conditions. Or the subtlety that I decided to avoid, what are called twisted boundary conditions, where a sign flips as you go around. Again, don't worry about the precise definition. But the key thing by both of those boundary conditions, this is where the Lth site interacts with the first site. But then the thing I started doing at some point, I forget which order I said these things, sorry. Luckily, that's not on camera. I noticed so if I'm really hand waving, I can go over here and no one can see me. So what I'm going to show you, in fact, for these open boundary conditions, there's a difference between this picture and the picture for open boundary conditions. So for open boundary conditions, what we find for the epsilon k, so it looks like that, both for h less than j and h greater than j. But here's the different thing. So for h, so let's say that's h greater than j, looks like that. But for h, what I'm about to show and make very precise is for h less than j, again, it looks like this, as you might expect. But there's one more. There's one at 0. And so that's why I sort of mumbled about there's this duality. And we know there's a difference between these two models. This has 2 ground states and that has 1. But there's one, well, we'll see exponentially close to 0, because I'll explicitly construct that. So that's what I'm going to show now and be very precise about. It's good. Any questions on this or on what I said at the end of last time before I compute some more? Okay, so here we go. So let's again look at this extreme limit. Okay, let me leave that up because that's important. So let's go to this extreme limit where h equals 0. So remember, in terms of then the Hamiltonian, so this is exactly what I just showed a little while ago. This was just then the sum 1 to L minus 1 of the sigma zj, sigma j plus 1. So then it's sort of obvious why they all line up in that limit. But if I rewrite that in terms of the fermions, remember what this was. This would be j times I psi 2j plus 1. And let me draw, remember I drew these pictures before. Okay, so the 2 dots, this is one side of the original lattice, and then these are the 2 fermions, the 2 Majorana fermions at each point of the original lattice. Okay, well, see, notice, so now the J ones went like this. I think I drew them. Those are the J couplings. But you notice one huge difference between the H greater than J, or sorry, H equals 0 and J 0. So they're all fermion bilinears. But in this case, with open boundary conditions, these guys don't appear in the Hamiltonian. So psi 1 and psi 2L H in the Hamiltonian when little h is 0. So it's big difference. And remember, the Hamiltonian's fermion bilinears. Fermions anticommute, different fermions anticommute. So therefore, psi 1 commutes with the Hamiltonian when h equals 0. And same for psi 2L, the ones on the two ends. So that's psi 1, that's psi 2L. So they commute with the Hamiltonian. So if you look at the definition, remember psi 1, if you look it up, what I defined, remember it was the string behind it, but on the first sight there is no string. So psi 1 is just sigma 1z. And then if you write it out, remember psi 2 L would have been minus I sigma LZ product of K less than or equal to J. But that's L. Did I have this nasty thing. Did I write out this properly last time? I did write it? Okay, good. I hope so. I have this nasty feeling I didn't write that out. So, sorry, K less than or equal to L. Right. But this thing now for 2L, so is K less than or equal to J in general. That was the thing I was worried I didn't write out properly. But then, so this thing is just this minus 1 to the F. Right, so this is just minus I sigma LZ minus 1 to the F. And so now let's look again in this limit. We had our two ground states. Remember, there's the plus, which I took as all the ups. So let me just write it this way. Plus and minus was these two linear combinations. Okay, but now if I take psi 1 on this, so psi 1 acting on plus, well, it just measures the spin of the first one, which is that one or that one. So psi 1 plus equals minus. Right? And likewise, psi 1 minus equals plus. It has to be. Remember, psi, each of them square to 1. So, and if you check now psi 2L on plus, well, it gives you minus, but there's that I there, so probably gives you maybe minus I times minus. I might have got those signs screwed up, but extra credit if you manage, if that sign is wrong. Someone finds that out. But anyway, up to the sign. So what's psi 1? And so remember, we can't, even though psi 1 and psi 2L commute with the Hamiltonian, they don't commute with minus 1 to the F. So we can't simultaneously diagonalize H minus 1 to the F and psi 1 and psi 2L. So I've chosen to diagonalize minus 1 to the F. Right? Remember, so then what they do, so psi 1 and psi 2L toggle between the two ground states. And this is what I would call a fermionic zero mode. Fermionic because, remember, these anti-commute with this minus 1 to the f. So what minus 1 to the f is really is measuring fermion number mod 2. I'll say a little, when we talk about superconductors, I'll say a little bit more about that. Any questions? So this is all so far after the break, I'm discussing only the extreme limit h equals 0. Any questions? But now let's go for h greater than 0. Well, what happens? So there's some off diagonal terms in the Hamiltonian. Like I said, the ground states split, but we can actually compute exactly what's going on here. And, well, so let's do that. So, right, I'm sure I said everything I needed to say. So you could so you could diagonalize this matrix I wrote down, you know, the one with the hj minus hj, that one, and you would find that there's an eigenvalue and remember, since we're doing open boundary conditions, remember I made a point last time, for periodic, there's somebody down in that corner down there, but for open boundary conditions, there's nobody down there. L and 1 don't talk to each other. So you would find an eigenvalue close to 0. So you can do that. It's not that hard. But to see what's going on, we don't even need to do that. Because let's now ask the question, okay, so when h equals 0, psi 1 commutes with the Hamiltonian. All right, but now, that's psi 1 at the end, but now I add this coupling in with little h, it obviously doesn't commute with that anymore. So, let's ask now what happens when we do commute h with psi 1. Now full h, no little h equals 0. Well, any term that doesn't have a psi 1 in it still commutes with it because it's a bilinear, or psi 1's a linear, so they'll commute. The only term that doesn't commute is the one that's IH times psi 1, psi 2. Right? Is that clear what I just went there? Every other term commutes, so I can forget all those other ones. It's just that first term that doesn't commute. All right, what's that commutator? Right, minus IH psi 2. I think that's minus sign's correct, right? Because you have to, remember they square to 1 and they anti-commute. So commute that through. I think there's a 2 as well, right? All right, everyone okay with that? So it doesn't commute. So that looks bad, but it's still, notice, remember, commute a bilinear with a linear, you always get a linear. Well, that's the linear, the psi 2, and that's the coefficient. But now notice something. If I take the combination psi 2, psi 3 with psi 3, what's that give me? What's that commutator? Sorry? Yeah, 2 psi 2. Well, yeah, 2. Take a vote, or what's 2? I think it's 2 psi 2, right? Because these just squared 1, right? So that's 2 psi 2. So now the trick is, well, notice psi 3, that term also appears in the Hamiltonian. Psi 3 commuted with something gives you psi 2. So if I arrange it right, I can stick something else in and cancel that. So more precisely, if I write down the Hamiltonian h1 plus h over j psi 3, all right, well, h psi 1 gives me that h minus 2i h psi 2. Well, then this, remember, this term appears now, will appear, there's a I, j, psi 2, psi 3 term in the Hamiltonian. So that gives me exactly what I want to cancel the psi 2. So those terms cancel. So let's write that out. So that will give me my minus 2i h psi 2. But then I get plus h over j times I j 2i j psi 2, right? Coming from the next term in the Hamiltonian, right? Is that clear? Where that term came from? We're not quite out of the woods. What other term do I get? So the two terms I wrote are correct. So remember what the Hamiltonian is. Well, written it out a million times, h equal. Right, that's the Hamiltonian written in terms of fermions. So the psi 1, psi 2 term gives me that. The psi 2, psi 3 term gives me that, which nicely cancel. So that's good. So those go away, but I haven't quite finished. What other term? Right, so it'll be something with psi 4, right? Because I've got a psi 3, psi 4 term. So in fact, what I just get is basically the same as this, minus 2i h psi 4. But here's one thing to notice. You know, if we're in the ordered phase, h over j is less than 1. And so now if I do this again, oh, yeah, sorry. Good, thank you. Yeah, thanks, Jay. Right, so I got the h from there, but then there's an h over j from there. So that's right, it's h squared over j. Good, very important. Thank you. So this is h over j. But then notice, so now h over j is smaller than 1, so this thing is getting smaller if we're in the ordered phase. So if we keep going, we can now add a term psi 5, right, which will cancel this, give me psi 6, just keep going down the line. And so what we get now, if we have now the commutator h, psi 1 plus h over j, psi 3, plus psi 5, and well, eventually we're going to run out of system, so we have to stop at the other end. But we go down to there, and then we just simply get minus h over j to the L minus 1 h psi 2L. With a factor of 2, thank you. Yeah, good. But notice the coefficient of this. If h is less than j, this is exponentially small. So that's what I meant before the break when I said that. It doesn't matter how close it is, as long as L's big enough, that gets minuscule. So this thing almost commutes with h. And by almost, I mean to these exponentially small corrections. And if they're an infinite size, if you want to be an infinite size, it just commutes. But this anymore. So one important thing we should check, though, so remember now, but remember psi 1, when we were at h equals 0, psi 1 toggled between the two ground states. So I said these exponentially split. So if I have these two states that I call plus and minus, well, this operator, let's call this operator capital psi. So psi acting on plus gives me something proportional to minus. And let's work out what that constant of proportionality is, plus some exponentially small. So we can work out, so we can now take, let's just take the operator psi squared. Right, so this is just that operator. Squared. So what's that? Once you get used to Majorana fermions, you can start to do these things in your head. So what's that? Yeah, it's the square of every term, right? Because the other terms, if I take this term plus that, but I got two of them, and I get a psi 1, psi 3, and then I get a psi 3, psi 1. So those all cancel. So this is nice. So that's 1 plus h over j squared plus dot, 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 all the way up to h over j, the 2l minus 1. So we can sum that up if you want. And there you go. So if we can now just normalize it by that thing, so as long as h is less than j, that series converges. So let me now just define the operator psi 1, and the reason for the 1 will be apparent momentarily. That's just equal to psi times this stupid normalization factor. I guess it would be 1 minus h over j squared, 1 minus h over j, 12 minus 2. And so then psi 1 squared equals 1. So we found another Majorana. And remember this, if you just diagonalize that matrix, you would find this. There would be corrections because to get rid of that exponentially small bits. But you would find this exact same thing. And so what we just did here was normalize the eigenvector of that matrix, if you wish. But you don't, let's say, you don't even need any of that fancy stuff to get with this. This is all just completely elementary manipulations. And so now we can indeed say we have these two, quote, ground states. One of them isn't quite a ground state. So we have psi plus equals minus, these corrections, small corrections. And if you want to work them out, you can then get. But see, since there's these corrections, the energies are split. One thing to note that I'm going to discuss probably lecture number 4 in a little more depth. I mentioned the ground states, but this is actually true for the entire spectrum. So it's that by some h over j to the L, so order h over j to the L. So one of the things I've been just talking about ground states, but this is actually true for the entire spectrum. because this is an operator. So this is what I meant by when I drew this picture before. Now, there's an operator here that you can either fill or leave empty if you want, but it's exponentially small in energy. So it only shifts the energy whether you fill, remember, so the energy is, plus or minus epsilon 1, plus or minus epsilon 2, right? But if I have an epsilon 1 that's almost 0, that means all the energy levels are only split by this tiny epsilon 1. So this zero mode does more than just say that the ground state's the same. The zero mode says that all the energy spectrum in the two sectors is the same. So if I plot the energies now, so I have minus 1F, remember, this commutes with the Hamiltonian. So I can diagonalize at the same time and look at my two towers of energies. Well, I've got a ground state there. Well, then there's another ground state there with energy only exponentially close. And then same for the first excited state, same for everything. Even once you get up here and these levels get exponentially close, you will see another one exponentially close, do it over there. And that's an exact statement. And this is something that we named recently a strong zero mode. So just wanted to comment here, and I guess probably not next time, but the time after that I'll say a little bit more about that. Well, so what we define a weak zero mode. So yeah, to get ahead. This is something. So I haven't talked. Remember, I said in the title of the lectures is something about topological order. I haven't said anything about that today. Maybe I'll probably get to that by the end. At least say a few words. What we mean by weak zero mode is something that just relates the ground state. So for topological order, which I haven't introduced yet, but I will, all you need is this ground state degeneracy. And so, and there are cases for which you don't have this pairing of the spectrum, but you have it just down here, and so that's what we call a weak zero mode. No, see, this isn't, so an important question. This is not a symmetry. So it is away from, so at h equals 0, this extreme limit, it's a symmetry, commutes with the Hamiltonian. This doesn't quite commute with the Hamiltonian, right? Because remember, when we compute the raising and lowering operators, right, we get something like, we get exactly this. Okay? So if epsilon k were exactly 0, this would be a symmetry. But this is now, I'm saying it's exponentially small. Okay? So it's not 0. So it's not a symmetry. It's a weird thing. I mean, so you shouldn't think of this thing as a symmetry. It's an operator that takes a level from here to here. And so I'm saying in there's topologically ordered cases. In fact, I'll talk about this with interactions and all that. Sometimes what happens is, these just all go any which way, but the ground states stay degenerate. And sometimes this happens. So I'll talk about that. Good. Any other questions? Yeah. Right. No, not necessarily. No, there's just two parameters. That's a fascinating question that actually so if you just look at numerically, actually even in icing, so if you just take the icing levels and look up there to see what happens, it turns out these spacings are uncorrelated. In other words, you can get like 3 in a row. If you list them all in order, the splitting due to this thing can be larger than, because the thing about icing is the sum of all these epsilons with pluses and minus signs. So obviously sometimes those will cancel and you'll get two levels really, really close together just by accident. I mean, so this scale is not, in fact, even for icing, it is generic. I mean, it can be larger, can be smaller. I mean, this one fluctuates. If you talk about, think of this as random matrices, there's all this eigenvalue spacing, so it's just a statistical thing. You'll get things that are really, really close together and things that are further apart. This is in a sense random, whereas this is not random. Yeah. No, it's important. It's something that confused me for ages until I just sat down and looked at the levels one day and said, no, they're just totally different. Yeah. Yeah, sure. Right, that's what I'm going to do next. Okay. Yeah, you can get the same thing. Right. So good. Perfect segue. Right. So what I just talked about was psi 1, but remember I said at the other end I can do the same thing. So remember at little h equals 0, remember we had h at h equals 0 commutes with psi 2L, the other end. Remember that other guy was there. That commuted. Well, I again add the full Hamiltonian in. It doesn't commute anymore, but I can do the same thing. And so that's the reason for the superscript. So now I can define a psi 2, which is equal to this annoying, well, maybe annoying, but really important factor. Times, well, psi 2L, and then plus h over j. Anyone want to guess what the next one will be? 2L minus 2, right? Remember that's important, is you'll 2L minus 2 plus so forth. H squared 2L minus 4. Well, so the reason why I made a point of that is to note now, these are all the even ones. The other one involved all the odd ones. So there's no psi that appears in both. So, very important, and not immediately obvious at all. But so if I define that psi 1, psi 2, these two anti-commute. If they had involved the same ones, there would have been these annoying terms that didn't anti-commute. So that's really important. So these only even, whereas the other one only involved the odd. All right, but this toggles as well. So we have this system here, and psi 1 does this. But then psi 2, the one at the other end, does that as well. So it's a quantum, so if we now go, so what people then like to do, especially when thinking about topological order, is, so now you make the gap very big. So you're more precise, work at energies. So this turns out to be, this is somehow, the limit h much smaller than j, but not 0. Okay, then let's just, and say if we choose to confine ourselves, not worry about these states there, we can just think about these guys. And so we have a quantum two-state system. Plus and minus. Their energies are the same up to some very tiny exponential correction, so you can write an effective Hamiltonian if you want. I won't bother. At least not now. We're not going to use that. All right. Quantum two-state system that I call plus and minus, and we have these operators where psi 1 of plus equals minus. And since they squared a 1, it just goes back, and you can work out the other one. And psi 2 of plus gives me minus I minus. You know they have to do something different because they anti-commute. If they did the same thing, they wouldn't anti-commute. They anti-commute. And so this is, so these are, so you have two Majorana zero modes, but the really interesting thing is, so we have two Majorana zero modes in a two-state system. Okay, but here's the catch. The zero modes are localized in the fermionic language. Because remember, for example, we had psi 1 to that annoying constant. So very crucial. This thing is falling off. Very crucial that h is smaller than j, and this thing will exponentially fall off. So now here's an important piece of physics. So this is why I said it's been renamed to the Kitaev chain. Well, if you take the Ising model as a model of spins, these operators are horribly non-local. They're worked out. This whole story I just said, this picture I just said was worked out by, it's implicit in earlier than this, but it was very explicitly worked out by Feudy in 1970. Everybody knew this, and again, the experts that studied this. This was known long, long time ago. But now, nobody really asked, well, what happens now to these sorts of operators in the fermionic language? This is now localized at the opposite ends of the system. So we've spatially separated these two zero-mode operators. And so that's really fascinating. So you can think of these as separate particles, right? I can do something locally. I can do whatever I want locally. I can make this operator locally, right? I can do psi 1 locally. And in the fermionic language, I'll write down things explicitly, but let me just say it in words first. So I can do something locally at one end with the fermions, and that changes the whole system. But I can do something at the other end, but it does exactly the same thing to the system up to these phase factors. Well, no, so, okay, right. So experimentally, it's easy. So I can inject a fermion at the edge. So hold that question, because let me make sure I didn't want to say anything else first. Okay, no, this is precisely, this is precisely the point. Okay, yeah. Okay, good. Hold those questions. Let me just look at my notes and make sure there's nothing else I wanted to say, because that's next topic. Any other questions on this before that aren't similar to those questions, because that's exactly the next topic. Okay, good. Let me just look to make sure there was nothing else I wanted to say on this bit. All right, good. No, so let's say, all right, good. So I've set it up here. We've got a two-state system. Again, forget all this other stuff. We're at low energy, so we never worry about those levels. We've got two states. We've got these two operators, but they're localized. But now let's think back to the free Fermi systems that I did before in the last lecture. Well, one thing I can do now is rewrite, let me get the definition precise. I can define an operator. I want to write it, sorry. So let's define an operator C sub j equals e to the I phi over 2. Over 2. Okay, so C is a definition. C dagger is just the dagger of that. Can throw in a phase, because why not? Well, this satisfies exactly the anti-commutation relations I wrote in the very first lecture. So CJ, CJ prime, dagger equals delta JJ prime. And then, I don't even remember if I wrote this out the first time, but I should have. If I didn't, the different ones anti-commute. I think I may have said it, but I don't remember writing it. Anyway. So it's easy to check that from these fermions, in particular, let's do one in our head, you square this, you get 0, right? Because that squared is 1, this squared is -1, and then the other one you get psi 1, psi 2, but then you get plus psi 2, psi 1. So those things. So you yeah, let's also c squared equals 0. Well, okay, so this is what I was starting to get at and what these questions addressed. We have this quantum two-state system with these two operators. Well, to toggle between these two ground states, if we now think of these as real physical fermions, well, these are localized, right? C1 is just, well, psi, so I can then just rewrite, obviously. Yeah. Someone say something? Oh, okay. So psi, let's write it out again to be pedantic. Psi 2j minus 1 equals e to the I phi over 2 cj plus e to the minus I phi over 2 cj dagger. And you can write down the one for psi 2j as well. So now let's think, if we insert this in Ising, so here's another homework problem. If I take the Hamiltonian now, so this is a pretty easy one given all that we've done so far. Just do this for open boundary conditions because you don't have to worry about so using that definition I just erased. So we take the following fermion Hamiltonian. Oops, much too big. HC is Hermitian conjugate. I guess I have to put another sum here if I want to do open boundary conditions. Okay, so first, now a trivial exercise is to show that this is equal up to signs, if I may have screwed them up, but oops. So this is going to be, this is all still fermion bilinears, but it's going to be slightly more general than Ising. Let me write it all out. Again, up to signs, maybe some factors of 2, but I think I got it right. So the one thing this goes beyond Ising is there's a sigma y, sigma y. So to get Ising would be delta equals t. Oh, because that's a typo. Thank you. Good. Any more stupidity? Like I say, sign. Well, maybe I got the signs right, maybe I didn't. But that's part of the homework exercise to correct my signs and twos. But maybe it's right. I should mention, this I stole straight out. There's some really nice review lectures that cover this and what I'm going to be saying. Many of the things I'm going to be saying in the next lecture. There's a review article by Jason Alicia. It's in 12. It's on the archive. I can't remember. 1203 maybe. Lots of review articles, but this one I found particularly aligned with the kinds of thing I'm saying. Okay, so all right, so let's unpack this. This looks ugly. All right, so here's the thing now. Remember our Ising Hamiltonian, which I won't write down since I've written it down about 50 times today. Remember, has the psi 2j plus 1, and the psi 2j minus 1. But notice psi is this combination of C and C dagger. So if I take psi 2j minus 1 times psi 2j, which also has a C and C dagger, I get terms that are CC. Right? So that's these terms there. Because notice I said Ising, the sigma y vanishes, so this term is gone, but that corresponds to delta equals t up to this phase. So in Ising, and this fits because you remember the first one we did, just the plane hopping has a U1 symmetry. Particle number is conserved. Here, fermion number F is conserved only mod 2. Right, because I can create or annihilate two fermions at the same time. Okay, but what this suggests now, there's actual condensed matter physicists here. When you have Hamiltonians that look like this, what do you think, or what ought you think? Come on, don't be shy. I know all, yeah, superconductors. And so what you can do to really make these things, it's a little subtler, it's much subtler than what I'm saying, but very schematically, what you can do, you have some wire. So we've got our hopping fermions, so that'll give us that term. This is just the hopping term I wrote down very first lecture. This is just the chemical potential I wrote down. So you have a wire, you got both of those things. So you just trap fermions. Fermions exist in the real world. Trap them in a wire, but then you put a superconductor near it. I understand this is easier said than done, but it is done. And then you couple this in a certain way. You need spin-orbit coupling, et cetera, because I'm doing spinless fermions, and real fermions have spin, so it takes a little work. But to get this, but it can be done. And that induces, so a superconductor, so a proximate superconductor induces this pairing. The C dagger terms. So this physical system can really be made and having nothing to do with spins. But so now here's the beauty. These are fermions, they're real physical things. And if we have our wire here, so now we've got our wire here. Everyone who's going to do the homework got that down so I can. So I've got my psi here at one end of the wire. Sorry, it's my psi 1, my psi 2 at the other end of the wire. Well, so these are separated physically, but it's still just this two-state system. And so when I do, so now I can answer these questions. When I do something locally, well, I can just inject a fermion here, right? That operator I wrote down in terms of the fermions is totally local. So I can just do something here, but it changes the state of the entire system. I mean, that's okay. I mean, you can do something locally and change the state. We saw that before, right? Because remember, recall psi 1 is just sigma z1. But then psi 2 had that big string. But here's now one of the spectacular punchlines of all. So all that's pretty cool. But now you think about, all right, so I made this big point to say the states are split just exponentially in energy. If I make this big enough, it'll go. But now the big question, and what I'm going to address next time, in more quantitatively, yeah, good, all right, so this is perfect. So I can just now say some qualitative words. and fermionic. Fermionic system. So if your fermions are your real physical degrees of freedom, these things are robust in the following sense. Well, so you ask, well, what if this were really a spin system? I wrote down that Ising model. I have, looks like 2 ground states, and they're only, if your system is 1,000 sites long, that coupling, is completely negligible. So you have 2 degenerate ground states. But you ask experimentally what might split them. So for spins, some stray magnetic field, H, let's not use H. I'm going to use all these things. I don't want to use capital H because that's the Hamiltonian. What's another? B, yeah, this is bad. This is so not B, mu B. There we go. We can write dielectric constant. Permittivity. Anyway, so mu B times just some site sigma. Something happens. There's just some random magnetic field. I mean, you can't control these things. At some point, this will split the 2 ground states. And if you have a lot of, magnetic fields, they're clearly split. They're not going to be degenerate at all. It would be easy to detect experimentally the difference between the 2 ground states. And for our fancy topological purposes, we don't want that. But in the fermionic system, so if we've built the identical Hamiltonian, but our physical degrees of freedom are fermions, then this term won't happen because this is non-local in terms of the fermion. Sigma Zj, so it's not only non-local, but in fact it's an odd number of fermions. Sigma Zj will be up to some i's, like psi 1, psi 2, psi 3, all the way up to psi 2j minus 1, up to some sign. Something like that. I's or signs. So this isn't going to happen in a physical, if fermions are. So you get the control by having these being able to toggle by just doing something here. You can make that 1,000,000 miles away. Well, okay, a few nano somethings away. But far enough so you can just totally manipulate that, ignore that, but change the toggle between the states and do the same thing over here. So, and it's robust. And moreover, and what I'll get through next time, is when you do this, you can get non-abelian statistics by this sort of manipulation. Okay, so I'll stop there. Thanks. Quick questions? Or, yeah. Yeah. Yes. Yeah. Absolutely. That's a future, like either the end of next time or lecture 4. I'm going to talk about that. So the short answer is it's robust, even against interactions, at least for the ground states. So that's I'll at least for the ground. You'll still have the 2 ground states only exponentially split. Yeah, good. All right. Oh, yeah. Yeah. Well, you can presumably form combinations of the 2 that are, well, I mean, no, yeah, right. No, you can't. I mean, yeah, this is a combination. No, sorry, yeah, that's right. This is a combination of the 2, and so that's why acting at one end will change the state of the whole. So obviously, you can think of operators that do stuff like slosh the fermions around. This is like anomaly physics. You can move stuff around. But I'm not. They're definitely a highly entangled state. But I mean, they're highly entangled. We can obviously manipulate that state by doing things that, I mean, because they're entangled, obviously we can manipulate. But you can't think of it just as a fermion in this end versus a fermion at that end. Or at least, I don't have a good way of saying that. Yeah, it's definitely entangled. Yeah. No, so there's two spacings involved. So the random matrix, if you wish, would be within each symmetry sector, right? Because you can diagonalize -1 to the f. So that means so even if you want to think of it as a random matrix in some class, there's that. So this is very special, by the way, to open boundary conditions. Okay, this does not happen for periodic. That's why I made that point at the beginning of the hour. So then that's just some random matrix problem, although it's constrained. You're only within the -1. And then within there, that was just supposed to evoke, what happens there. There's, think of it as some random matrix. Of course, in this case, it's not a random matrix. We know exactly what the matrix is. We can even diagonalize it. But you may or may not, well, actually, yeah, it won't be really a random matrix because there's no interaction. So but if you don't know anything, it'll look like a random matrix, put it that way. And so you'll just see, these things will space and they'll not space, and you won't see any regular pattern. You have to look at these subtler things. That was my point. Whereas if I look at a level here, I know within some exponentially small thing, I will always see another level here. So whatever random stuff is going on, quote random, it's not random, but it appears. And in cases with interactions, so I don't know of any cases with interactions that aren't integrable. So there's an integrable case where that has this, and so they go up and down together. It'd be fascinating if there were non-integrable cases where they all go up and down together. Then it would be something where... Oh God, I can never remember which class is which. Yeah, so I failed. So you can argue it out and tell me next time whether this is D or BD1. And what is it? Anyone know? Is it B or should we take a vote? Yeah, everybody vote. Is it B or D? BD1 or D? All right. Okay. Yeah, it's BD1. Okay.